Now I want to discuss the pooled standard deviation. As I told you, now we have a two sample. Here's a sample number 1. Here's a sample number 2. And now here is the S1 square, is the S2 square. By the definition, the S square was the variance, right? Simply we just take the square root of it, it will be the standard deviation. So the variance will be without the square root sign, but take the difference, square, summation, divided by n minus 1. Definitely the second one from the second sample, so I can plug 2i x2 bar divided by n2 minus 1. Exactly same way, I can take the s1 square, which will be the summation of x1i minus x1 bar square over n1 minus 1. Exactly same way. It's good, right? Let me compare to the pooled standard deviation. The pooled standard deviation, which was the square root of n1 minus 1 s1 square plus n2 minus 1 s2 square over n1 plus n2 minus 2. Can you remember the SP? It's a pooled standard deviation. So now let me erase the square root sign. Then I have to take square. Now I call it pooled variance. Without the square, without the square root, with the square, it is the variance, pooled variance. Let me modify a little bit. I can split the degree of freedom, which will be n1 minus 1 s1 square plus n2 minus 1 s2 square, n1 minus 1 plus n2 minus 1. Can I split n1 plus 1 and n2 plus 1? Yeah, when I add them up, it will be n1 plus n2 minus 2. Please compare this one and this one. This one and this one. See? When I plug s1 squares into here, let me take this part. So n1 minus 1 s1 square over n1 minus 1. Simply now, it is s1 square. It's the same idea. Absolutely, mathematically, it is not exactly same, but roughly I explain to you. So it's n2 minus 1, s2 square over n2 minus 1. Then it's just s2 square. So roughly I can say, mathematically it is not exactly same, but roughly I can say it is S1 square plus S2 square, roughly. But exactly, we have to plug this one, I mean the right-hand side, and we plug this another right-hand side is into here. So let me try. Exactly. Then now, exactly, it will be n1 minus 1 times, see, I have to plug this one is into here. So that is the n1 minus 1 summation x1I minus x1 bar square. I mean at the top. And let me erase. I need a space. And here is a n2 minus 1 times. Now I have to plug the S2 square. S2 square here is another summation of x2I minus x2 bar square over n1, n2 is minus 1. And then what? Divided by n1 minus 1 plus n2 minus 1. So n1 minus 1 and n2 is minus 1. So far so good? So now I just plugged what was S1 square and what was S2 square mathematically. They are now exactly same. Exactly. But now look at this. Here's a n1 minus 1. In the denominator, there's a n1 minus 1. Cancel out. n2 minus 1 and n2 minus 1. We can cancel out. Then now, exactly, mathematically exactly, it will be summation of x1I minus x1 bar square and summation of x2I minus x2 bar square over n1 minus 1 plus n2 minus 1. You know, it is a form of the sum of squares divided by the degree of freedom. It is the exactly same form as the variance. Always the variance has the form, the sum of squares divided by the standard deviation. Look at this. It was a variance number 1, sum of square divided by its degree of freedom. It is the second variance, has the form sum of square divided by its degree of freedom. Now we pooled two samples is together. We merged two samples is together. So now here sum of all together, I mean the sum of all squares, sum of square from sample number 1 and sum of square from the sample number 2, and then take the sum again. It's not only the sum of squares, we take the sum of the degree of freedoms. It's the sum of the two degree of freedoms. So finally, we have the form, the sum of squares divided by the degree of freedom from the pooled two samples. It will be the SP square. So finally, we can define the SP squares. So simply we just take a square root of it. That would be SP. So we use the pooled standard deviation in the pooled t-test